Greetings, inquisitive minds. I am Professor Energy, your guide through the intricacies of thermal energy reservoirs. But fear not, for we shall make this adventure both enlightening and entertaining. So, what exactly is a thermal energy reservoir? It's a vast interconnected network where energy is stored and exchanged. It's like a bustling metropolis of heat, where the flow of energy is governed by the mighty second law of thermodynamics. The second law is the grand conductor of this extraordinary symphony. It states that energy spontaneously flows from regions of high temperature to regions of lower temperature, seeking equilibrium. Picture a cup of hot cocoa left on a table. What happens? The cocoa loses heat to its surrounding, becoming cooler over time. And that's the second law in action, my friends. Meet our thermodynamic heroes, Hot Harry and Chilly Charlie. Harry, the high temperature champion, yearns to share his energy with Charlie, the cold temperature contender. And following the second law, energy flows from Harry to Charlie until harmony is achieved.
Fantastic, isn't it? This natural flow of energy enables
Wow.
us to harness its power and perform remarkable feats. Behold the steam turbine, a true marvel of engineering. By utilizing the energy from a thermal energy reservoir, we can transform it into mechanical work, propelling this turbine into motion. And through wonders of electromagnetism, this mechanical work can be converted into electrical energy, illuminating entire cities and powering our technological marvels. Now, my esteemed scholars, let's dive deeper into the maths and science behind this concept. Equation and diagram will help us unravel the intricacies of thermal energy reservoir, providing us with a solid foundation to conquer new frontiers. As you venture forth in your academic pursuit, remember the wonders of thermal energy reservoir and the second law. They serve as the bedrock of countless scientific and technological advancements, shaping our world as we know it. Farewell, intrepid learners. May your thirst for knowledge continue to illuminate your paths. Keep exploring, keep questioning, and unravel the mysteries that awaits you in the captivating realm of thermal energy reservoir.
Thermodynamic temperature scale is a temperature scale that is independent of the properties of the substance that are used to measure temperature. And this temperature is called Kelvin scale. As for the temperature that on the scale is called the absolute temperature. So as we can see in the figure 6.43, the temperature ratios depends on the ratio of heat transfer between a reversible heat engine and the reservoir and independent of the physical properties of any substance. But the thermodynamic temperature scale is not completely defined because it only gives us a ratio of absolute temperature. So we also need to know the magnitude of a Kelvin. So in 1954, the triple point of water was assigned as the value of 276.16 Kelvin. So the magnitude of a Kelvin is defined as 1 over 273.16 of the temperature interval between absolute zero and the triple point temperature of water. So the temperature on these two scales differ by a constant 273.15. So how to obtain in temperature in degrees Celsius? So from the temperature given in Kelvin, we can subtract 273.15 from the temperature given because 0 point on Celsius is the freezing point of water, whereas 0 point on the Kelvin scale is absolute zero temperature.
A hypothetical heat engine that operates on the reversible Carnot cycle is called the Carnot heat engine. The thermal efficiency of any heat engine, reversible or irreversible, is given by this formula. Then the efficiency of a Carnot engine or any reversible heat engine becomes this formula.
This relation is often referred to as the Carnot efficiency, since the Carnot heat engine is the best non-reversible engine. This is the highest efficiency a heat engine operating between the two thermal energy reservoirs at temperature lower and higher temperature can have. All irreversible heat engines operating between these temperature limits have lower efficiencies. An actual heat engine cannot reach its maximum theoretical efficiency value because it is impossible to completely eliminate all the irreversible associated with the actual cycle. The thermal efficiency of actual and reversible heat engines operating between the same temperature limits.
Okay, now let's go to the figure below. From this figure, it shows that how the Carnot heat engine works. Okay, basically it is started from the high temperature reservoir at the temperature 1000 Kelvin. From this, it transfers heat to the Carnot heat engine. Okay, so now from the Carnot heat engine, it rejected heat to the low temperature reservoir at 300 Kelvin. Okay, so basically it is how the Carnot heat engine works. In addition, I want to tell you that the Carnot heat engine is the most efficient of all heat engines operating between the low and high temperature reservoir.
This is a Carnot example question between cold reservoir and hot reservoir. Given that heat energy of hot reservoir is 14,000 joule, temperature of heat reservoir is 700 Kelvin and temperature for cold reservoir is 400 Kelvin. First, we will searching for heat energy into cold reservoir, which is QC, by using formula of TH over TC is equal to QH over QC. So we substitute all the value and we get heat energy into cold reservoir is negative 8,000 joule. For the second question, we were searching for mechanical work in the engine by using formula W equal to QH minus QC and we get 6,000 joule for the mechanical work. For the last question, we will calculate the efficiency of Carnot energy, which is efficiency is equals to TH minus TC over TH. So we get the efficiency of this engine is 42.9%.
For this session, we will talk about the quality of energy. As we know, the second law of thermodynamics is that processes occur in a certain direction and that the energy has quality as well as quantity. For this figure, the vertical scale of high up has higher quality and on the bottom has lower quality of energy, which is 0. And here, if we know in this figure, if you have the temperature of 3000 Fahrenheit, you get between the scale. If you get lower temperature, you will get the lower quality of energy. So which means that temperature and the quality of energy go together, which is perpendicular to each other. Here, we will discuss about the temperature on shown scale on the left side. High temperature increases the quality of thermal energy, and for work and electricity, which is up here, the quality of energy are 1.0, which is the most valuable and we want them. The lower temperature thermal energy, which is when we cook. If we use 3000 Fahrenheit, it will become all burnt. Same goes as a hot shower. The temperature may be around 30 to 40 Celsius. That is low quality energy, which is good and it is what we need because it is cheaper and easier to get, convert, and produce. And at ambient temperature, we have a lot of energy in ambient. Air, the molecule of air is bouncing around, have a lot of energy there. But it has zero quality of energy, no value. So for the conclusion, we can state that the more of the high temperature thermal energy can be converted to work. Therefore, the higher temperature, the higher quality of energy.